Okay, hello. Hello. So this is a part one of the tutorial for how to run the hybrid Gadget 4 code that I have written. So in this part, we're just going to look at how to set up the linear response stage of the simulation. So at this point, no particle neutrinos are existing yet. In fact, nothing exists yet. We're first going to just run the CDM only simulation with the neutrinos completely modeled with the multi-fluid linear response perturbation theory. And I'm going to show you how to set that up. So the first thing to do is to get some kind of initial conditions for initializing the CDM particles information. So for doing that, we first need to get a linear power spectrum as z equals 0 for the cosmology you care about. You can do that various different ways, class cam, or if you manage to write your own Boltzmann code, that's also fine. You just need to get the linear power spectrum somehow. So in this case, I'm going to use class. So here I'm going to show you a particular cosmology that I'll be using as an example, which I'll call M0 nu 3 or M00 nu 03. Okay, so for this one, you set the Hubble parameter, the omega CDM, omega baryons, and if you're using class, then you'll be setting the NCDM species to be 3, each one of them single degeneracy. You can do with one species with degeneracy of 3, that's also fine. We set the temperature at a seemingly pretty random value, but what that does is that rather than having 3.0, rather than having any ultra-relativistic species to fill up the delta N effective of 0.044, we're just gonna increase the temperature of neutrinos to make the total N effective to be 3.044. Of course, this is completely up to you in your particular run, and as long as you're consistent throughout the entire process, it shouldn't affect things that much. And yeah, we're setting the neutrinos density, which determines the mass, or you can set the mass straight away. Both are fine. And here I set the primordial amplitude AS instead of sigma 8. So for running class, at least setting sigma 8, it takes class a few iterations to find out what the AS is before you can start doing the calculations, and it takes significantly longer. So setting AS helps class straight away get on with the calculation. And here the important part is to output the redshifts that you want. So you want to output at a redshift of 0, but also sometimes it's nice to just output a higher redshift so you can have some kind of mechanism to check, compare your simulation results. So here I'm just going to output a redshift of 0, which is one we want, and also 2 earlier redshifts for comparison. And here we set the root of the output. We'll not be turning on the nonlinear module for now, so we're just looking for purely linear results. And to ensure that your power spectrum is as good as possible, you're only running class once here, so runtime isn't too much of an issue. You can run class with the parameter that you want, and then with a pkref file, which is a preset list of precision parameters that will ensure that your power spectrum will get to, I think, 0.1% accuracy. And you see it starts calculating, and here you can start checking some of the parameters to make sure they make sense. Like for example, your total N effective, it looks good enough. The temperature is not set exactly, so you get a little bit extra, but this is perfectly acceptable. And you can check that the mass of your neutrinos, or in this case, the non-cold dark matter species, these make sure that it corresponds to what you set out to do. And down here, these are very useful information as well. So check that the density parameters, so like the omega baryon, omega CDM, and your omega neutrinos, they correspond to what your intended cosmology is. And if you're running with the pkref precision file, it's going to take it a while, maybe 5 to 10 minutes to run class. And eventually you're going to get, so I'm going to stop running here because I already have it done. So eventually you're going to get, let me go to the place where I put the results. Okay, so eventually you're going to get a list of these files where you have the power spectrum and the transfer function for all the redshifts that you requested. So if you open one of these, for example, pkcb, you're going to see it's the matter power spectrum at redshift of 0, and it gives you 2 columns of K and P. If you're running with massive neutrinos in your cosmology, then you're going to get two power spectrum files. One is for the total matter power spectrum, so with all the CDM baryons and neutrinos lumped together as total matter. And another one is called PKCB, so that excludes the neutrinos and you only get the CDM and baryon power spectrum. Now, since we're initializing the power spectrum for only the CDM particles in our simulation, we actually want this CB power spectrum and not the total matter power. So we only want the the cold matter information. So at this point onwards, you need to pre-process this a little bit, not as much as you used to. So I do that with a mathematical notebook. So here I load in the power spectrum files that we just computed with class. So the CB, the PKCB for the three redshifts that we requested as Z0, Z49, and Z99. And here you can just have a plot to do a sanity check to make sure it looks correct and nothing really weird is going on. So this is the power spectrum part. But now, because we can't simply take the Z equals 99 or 49 power spectrum and initialize the simulations, because as we explained in other workshops where the relativistic effects and any radiation contribution is not accounted for in the n-body, so you have to do this whole scale back process. So in this case, we need to actually go and now compute the growth factor, the linear growth factor corresponding to our neutrinos. So here we go to what the new MFLR code. So that's the linear multifluid code that Amol has written. So here in this folder, you'll find three files. The make file, which it just contains very simply like find the path to your GSL libraries, make sure you have GSL installed, and show the make file where the path is so you can find it. And then the rest of it you don't have to touch. So you really only have to just change this path. And the other one is the pcu.h file. This is a very large file. Please don't try to open it. It's going to crash your computer. It basically just includes a whole list of momentum values for the Fermi-Dirac distribution that your multifluid decomposition is going to draw from. Now, the one that you do have to modify is this new mflr.c file. So this is the actual code. So in this code, you have to go in and modify pretty much 5 things. So the first one is the Hubble parameter. So this one has to correspond to whatever Hubble parameter that you had. So if we just pull up the class run that we had before. So here, just make sure your Hubble parameter goes in. Okay, where's the Hubble parameter in here? Okay, it doesn't list it explicitly, but then you should know what the Hubble parameter is. So put in the correct small h, so not large h0, but like the small h, so like 0.71 or 0.673, depending on what your cosmology is. And then you also have to tell her how much CDM and baryon density fraction there is today. So is your capital omega CB. And you can find it in here, so it corresponds to this non-relativistic energy budget, so that's the omega CB. So you can take this and you copy and paste it into here. And it also wants to know how much neutrinos there are. So this is the total amount of massive neutrino density. So here, the way I ran it with 3 NCDM species, so it's going to be one of these times by 3. So in total, it's going to be 0.006 omega nu. It also listed here as the neutrinos total budget, so you can actually just directly copy it from here. So that determines the cosmology. And now the n-effective parameter, again, it doesn't really matter, just be consistent. In here, we set it as 3.044. So here we're going to set it as 3.044. If you do a 046 or anything else, it's fine, as long as you keep consistent between these different stages. And then now the other two important one is the n tau and the n mu. So this tells us how how does the decomposition for the multifluid system is going to be done. So n tau tells you how many neutrino flows or neutrino streams there are going to be. So for the pcu.h file provided, you can go up to maximum 900. For running n-body simulation, you're very unlikely to get anywhere close to that because it's just too expensive. Usually 20 streams to 50 streams is perfectly sufficient. If your focus is on the neutrino part, perhaps set it higher to maybe 50 or 100 if you can afford it. N mu is the truncation of the multiple. So for each fluid is going to be tracked by a Boltzmann hierarchy, and this n mu tells us essentially at what order we truncate the Boltzmann hierarchy. And from if you look into the multi-fluid paper that we published, that n mu of 20 is perfectly sufficient to get percent level accuracy. Going higher, if you have the computational resources, it is generally recommended to increase the number of fluids rather than the number of multiples. It's cost benefit wise is more worth it to add additional neutrino fluids rather than tracking high number of multiples. Okay, and now comes down to the actual running. You scroll down to the very bottom. So here is set to calculate the growth factor. It's a bit hard to see with the single color, monotone color here, but there is this constant int that you set nk and nz. This tells the code how many k modes to track for nk. So here we're tracking 500 k modes, and nz tells you how many redshifts you would like the output at. So nz has to be at least 2. So you want it to be at a high redshift and one at redshift of 0. Because it needs to normalize the redshift to 0, so you always have to calculate z equals 0 results. So in this case, because in the class outputs, we computed for z equals 0, 49, and 99. So here we're going to do the same. So 3 redshifts, I'm going to compute as z equals 99, 49, and 0. And here, the next two constant doubles of k min and k max, this just tells you the minimum and maximum values of k you're going to be tracking. So here we're going from k times 10 to the minus 4 to k equals 20. Depending on your simulation requirements, this might change. For us, when we're running just a fairly standard half a GPC box with about 512 Q particles, this is a perfectly valid k range that covers more than what the simulation is going to cover. So is okay. But then if you're running a very small box, you will want to increase the k max and increase the k min as well. And this nk of 512 would just simply sample 512 k modes in between your k min and k max values. Okay, so these are the only things you want to change. If you want to increase more redshifts, you can just increase the nz and then add more redshifts into here. Equivalently, you can also increase or decrease the number of k modes. Usually 512 is perfectly sufficient for running n-body simulation. The power spectrum is fairly flat, not flat, like fairly featureless, so the interpolation between points is not going to be affected by the number of sampling points that much. Okay, so once you have set that, then you just simply run make. If it doesn't complain about anything, you should now see an additional binary file just called new mflr. So that's what you're going to run, just simply run new mflr. Now here, it's going to think for a bit to compute all the growth factors. This is an important piece of information. So this tau TeV lists the number of corresponding to the number of streams that you have requested for. So here we ask for n tau 20, so it's going to give us 20 values. And these 20 values corresponds to the momentum, the Lagrangian momentum of the neutrino fluids. And they're in electron volts. So you want to keep this because you need this later for initializing the neutrinos when you place them as particles. So I usually copy this and then save them into a text file somewhere. So here, show you specifications. So here I save them on the top of the text file alongside the class parameters. So I remind myself what this particular cosmology is doing. I'm gonna just quit this calculation right now because I have already done it. Once you let it run, I'll show you what it looks like. So once you finish running this multi-fluid code, you're gonna see this. So you're gonna get a whole list of values. This tells you at redshift of 0, k equals 20, whole list of values. So first one is the, actually I can't remember exactly what they are. It tells you in the .c file. So here, your printf, so this tells you what the printed out information is. So the first column is a redshift, so redshift of 0. Second column is the k, so k equals 20. And then it tells you the linear growth factor for the CDM, the baryons, so delta CB. And then third column is the f, so the growth rate, so it's the derivative of the linear growth factor. And then the final column is the growth factor for the neutrinos. And here, so at redshift of 0, because we normalize at redshift of 0, so here the delta CB, or the growth factor for CB is 1. So nothing really to see here. You don't really gain anything. If you scroll back up, now the next block of information tells us the output as Z of 49. Now Z of 49, this will be useful for us because it tells us the linear growth factor for the CB sector as Z of 49. And also, the next block is going to be Z of 99, where it tells you the same thing for the linear growth factor and the linear growth rate. So you want to just copy and paste these into a text file and save them somewhere. You'll need them for doing the backscaling. So here I have a folder called IC files where I save these as CSV files, where they're pretty much just, if I open one to show you, text edit, they're basically just these information, the Z equals 49 information, copy and paste into here and separated by commas. So now, yeah, if you load these growth factor information into Mathematica, you're going to get a bunch of, because each one of them has multiple columns. So you want to extract out of these the linear growth factor and the linear growth rate. So the D, the capital D, and the F for the CB. We're going to ignore the neutrinos for now because we're only doing the CDM and baryon particles. And once you plot them, you can look at a plot. So let's look at the Z99's growth factor, for example. It's going to be k-dependent because we're in a massive neutrino cosmology where the growth factor is not scale independent. So going from k of 0 to 20, that's the range we set. You can see you get your growth factor in this way, where, as expected, it's going to have some scale dependence on the around the free streaming scale. And then as you get to larger k, when the neutrinos are completely free streaming, it kind of tapers out. You can compare this growth factor to the growth factor predicted by class. So here I show you just taking the square root of the ratio of the class power spectrum between Z of 99 and Z of 0 and comparing this to the growth factor calculated by multifluid. You see that on large scales, they're a bit different, and on small scales, they agree with each other. This is expected, so we hope that on once we go into very small scales, close to a free streaming solution, the two is going to be the same. On the large scales, they differ because of the lack of radiation and the like metric perturbations that we're not considering. So this is the difference you're going to be seeing if you initialized with the class power spectrum rather than the backscaling method. So this is fine. Don't freak out if these two look different. They're supposed to. One's purely Newtonian, one is GR compatible. So you do expect them to be in disagreement. And if we look at the same comparison for Z of 49, the disagreement is smaller because there's now less time for them to evolve, so less chance of them to disagree. And now we're just going to simply rescale them. So I call the rescale power spectrum simply the Z of 0 power spectrum computed by class, the linear output, multiplied by the growth factor squared. Because one growth factor is going to scale the delta. Power spectrum is delta squared, so you're going to have to do the growth factor squared. And once you do that, you can double check, plot the rescaled, so the backscaled power spectrum, compared with the class's power spectrum at the same redshift as Z of 99. You'll see that you should expect them to agree very well on small scales because the growth factor agree well there, and see some disagreement on large scales. And again, this is due to the Newtonian versus GR difference, so again, it's perfectly fine. So now that's what you really have to do. So you have the rescaled power spectrum now, and for the new version of Gadget 4 with the hybrid module added in, we've done something different now. We no longer require you to format the power spectrum into that log base 10 format that the standard Gadget 4, the stock version, will require. Now you can simply supply the power spectrum in MPC on H cubed units. So we're just going to simply export these in 2 columns. So P table, so just in 2 columns of K and the P of K. And we're going to do the same thing for the growth rate, so the F. So here is the 3rd column, this growth rate file. We don't have to do any backscaling for this. We simply take the Z of 49 growth rate and we output them. So again, in 2 columns, in one column K and another column of this F, F of K. And now once you have these two, the way Gadget wants them is in two columns separated by white space. So here we have the power spectrum with K in the first column separated by a white space and P of K in the second column. Same thing for the F, K in the first column separated by a white space and F of K in the second column. And call these something that's recognizable. So in this case, I just call them M0 nu3 initial conditions, which is the power spectrum at Z99 and with 20 streams and 20 multiples. And M0 nu3 of the growth rate F at Z99 with 20 streams and 20 multiples. And now you can supply these two to the Gadget code for it to read in, and Gadget will then use these to initialize the CDM and baryon particles. Okay, so that's the initial condition file done. Now we want to load it onto our Gadget simulation. So here, let's go onto Katana. So on Katana now, let's go to the folder where I have the... Okay, here, so call it linear response, so linresp for the first stage. Now, we need to go upload these files into from our computer into the Katana files. So could just go to that quickly. 73 IC files, async AVH, the CB power, the IC, and the growth rate. Oh, oops. Okay, cool. So now you see these files on your Katana. And now you need 3 additional files for Katana to run the Gadget code. So first one is this outputs.txt. That just tells you at what redshift you want to output the snapshots. So this a priori, you probably don't know how to set it because you really need to determine when to convert the neutrinos to know when you want it. I've already done the convergence test, so I'm just going to go along for now. I'm going to explain the convergence test later. So here I'm just going to output at a redshift of 9. So this is a scale factor, so A of 0.1 for converting my first batch of neutrinos. And I'm going to do the other 3 outputs for later comparisons, so Z of 1, Z of half, and Z of 0 for comparing between hybrid and the linear response. But the important one is this, this A of 0.1 output where I'm going to actually convert the neutrinos. And yeah, and also it's just always a good idea to output at the first redshift at the initial conditions, so you can compare the first output to what you initialized with to make sure that everything matches up. And the other important one is the parameter file. So this is where you actually set all the cosmology. So in the parameter file, if we're running from initial condition, the linear response at the very beginning, and we're creating the initial conditions, you don't need an initial condition file. So here you can just leave it as the dummy file. Doesn't matter. Here it will want to know what the output file is called. So we just call it outputs.txt. That's where it's going to read the list of times to output the snapshots. If you call it something else, change it here. And important to set the time begin. So this is corresponding to where we want the simulation to start. We initialized at 0.99, so you're going to set to 0.01 for A, and time max is going to be at 1. Okay, now for the cosmological parameters here, most is going to be pretty much the same. So omega 0 still corresponds to the CB power. So this is, I'm just going to comment here. This is the CDM plus baryon density fraction today. And then the next one, omega lambda, that's self-explanatory. That's just the dark energy density fraction today. Although when you're running with the multi-fluid and hybrid, this parameter is actually redundant because the multi-fluid module sets the Hubble rate, and it assumes that you have a flat universe and assumes that you don't have any curvature and nothing else besides CDM baryons and neutrinos. So it's just gonna, as long as you set the CDM baryon density and the neutrino density correctly, then it's going to infer the dark energy density by just setting it as whatever's left over. Omega baryons, we're not running hydrodynamics, so we don't need it here. And we have two neutrino parameters for density. The first one's called omega nu part. That means it's the particle neutrinos. Now for this first section of just linear response, we obviously have no neutrino particles, so it's just set to 0. The next one's omega nu lin, that's the linear response neutrinos. So right now, that's going to account for 100% of our neutrinos. So set it to the same as what we had saved here in the class initial parameter file. And then the Hubble param is a small h, so make sure that matches your cosmology. So we had it as 0.71. And this is the Hubble, so if you set the small Hubble, you can just keep this as 100 kilometers per second per megaparsec. And then the box size is going to be the size of the simulation box in megaparsecs and h units. So here we're just going to set it to 512, so around half GPC. Now, the important one here now is the NLR parameter. This is an integer parameter that selects the method of linear response. So for NLR equal to 0, this is no neutrinos. So it simply does the standard CDM only simulation, so stock standard gadget. For NLR equals to 1, this does the super easy method. So you can look up on super easy paper on, it's basically a different neutrino linear response method. NLR equals 2 is the multiflow method. So for us, we want the multiflow method. So we're going to set NLR equals to 2. And you're going to keep it set to that for the hybrid runs as well. So you don't have to touch this. And now if we scroll down, we look at the ngenic part. So this is the initial conditions parameters. Grid size tells you how many particles. So here we're just going to set 512 particles. And we're going to have the two power spectrum and the growth rate files. So make sure these are named as the same that what we named before. So M003 IC for the power spectrum and F for the growth rate. And because now we no longer adhere to the stock standard gadget convention of reading the power spectrum, where now we just read the MPC on H cubed format, we also made it so that the primordial index, the NS parameter, is now redundant. So you can set this to the correct value to remind yourself what cosmology this is, but just remember that it no longer tilted, so it doesn't really matter what you set this to. It's not going to affect the input power spectrum. So yeah, once you have these set well correctly, then you can just leave this parameter file. And the last one is a script file. So this is just going to load the correct module. So this should be, I'll make another video about what modules you need, but it will be the same every single time. One thing's going to be different is setting the resources used. This is not so clear on how to calculate a priori. There is a guideline in Gadget 2 paper by Volker Springer. You can read that paper and it'll give you some idea of how to estimate the amount of, in particular, the memory resources needed. But Gadget 4 is slightly, from my experience, slightly more memory hungry than Gadget 2. So just remember to budget a little more than what you think you need. And also the multi-flow module occupies a little bit of memory footprint as well, but not that much, maybe like a few gigabytes. But I find that with 512Q particles, 60 gigabytes is perfectly sufficient. And about 40 hours of runtime on 32 cores, that's also sufficient. So if you have smaller boxes where you think the dynamics are going to be a bit more nonlinear, then you might have to increase the war time to allow it to have longer time to run. But yeah, other than that, everything else is pretty similar. So you just MPI run for all of the CPUs that you have, so 32 cores, so 32, and running with the Gadget hybrid binary and also with the parameter file. Okay, so the only thing missing now is the binary. So let's go to the Gadget folder, the Gadget code folder, and show you how to compile Gadget. So in here, you need to first go into the source code. So the folder SRC is where the source codes are. And in particular, you need to go into the neutrino folder to check the parameters there. So there's two parameters that you have to hard change and not set in the parameter file. So in the neutrino folder, there is the header file neutrino mflr.h. So if you go into that, You can see you're going to have, again, the ineffective parameter. Make sure this is, again, just consistent with how you set ineffective in the class and the growth factor calculations. Now, the two that you have to make sure you set correctly is, again, the n tau and n mu parameters. So if I did my growth factor calculations with 20 fluids and 20 multiples, I have to set it to 20 fluids and 20 multiples here. If you set them different, it's going to give you something weird for the neutrino results. Once you set these, you want to keep them the same. So throughout the hybrid run, you can pretty much set these and forget it. They will have to stay the same anyway. But then if you're running a different cosmology altogether or a different set of hybrid simulations, and you want to have more fluids, then you have to remember to come here to change this in the Gadget code. If you set it wrong, then it's going to give you wrong answers and it's not going to make any sense. So here is correct, 20 fluids and 20 multiples, so we're good. So we go back to the main Gadget folder. So now we want to look at the config file. So I called this one new config.sh. You could have your own config file called something else. There is a template one, so template config.sh, that includes all of the options. So you can go in there to check out what you need. But for now, for running hybrid, this new config gives you everything you need. So the first one is periodic self-gravity. These are standard for cosmological simulations. You have to set these. Make sure you unset the lean option, especially for the later hybrid runs, because the lean option forces all the particles to be the same mass. So that's not going to be good for us when we include neutrinos. So for us, we're going to not set the lean option. For PM grid, set the PM grid to be how high resolution you want the particle mesh force to be. Because of the FFTW conventions, you want to set this as a number that's 2 to the power of n to get the fastest calculation. So 1024, I find it kind of depends on your preference, but then the way I usually do it is to set this twice the number of particles I have. So I have 512Q particles, so I'm going to set this as 1024. Multiple order, so this is the tree force. So when you calculate the tree force, it expands the octree into multiple orders for calculating the gravitational force between particles. Stock standard Gadget 4 sets this to 2. It really doesn't really make a difference. I think from what I can tell in cosmological simulations, you don't gain much by setting multiple to higher order. It costs a bit more memory, so then we're going to be more efficient here and set it down to 1. So it's only going to store the monopole force for the tree, octree expansion. Now, this one's going to be a bit different. So normally, if you're running CDM only simulations, you only need the CDM particle type. But in this case, because we know we're going to later include neutrinos as additional types of n-body particles, we have to actually preset it to be higher. If we set this to be low and then we increase this later, Gadget is going to complain about the snapshots not matching up to each other. So I just set this to the maximum amount. 6 is the maximum that you can do in stock standard Gadget 4. So setting it to 6 allows to include the CDM baryon particles and 4 additional species of neutrinos. So preset this to the max. It doesn't cost you anything because if you have no particles there, it doesn't do anything. But then it allows you to increase the input particles later. And then set the power spectrum on output. So that means it's going to compute the power spectrum every time it outputs a snapshot. That's convenient, so you don't have to actually run any third-party power spectrum estimators. And ngenic, that's for the grid resolution for the initial conditions. So I usually just set this the same as the PM grid resolution. And now, if you're running the linear response simulation, you turn on this create grid option. So that tells Gadget 4 to put down particles and initialize CDM baryon initial conditions. And you want to make sure none of these 3 are turned on. So do not turn on additional grid, thermal velocity IC, or CB phase. These are for the hybrid run. So only turn on the create grid option. Okay, once you have set those, you can just simply type make. Now, Gadget's going to go through a whole lot of checks to make sure you didn't do anything illegal with the macros, and then it's just going to make the binary for you. You can make this here, as I've done, so it's just going to make it in the Gadget's home folder with a binary that you can then copy to wherever you need it. or you can make it directly into a directory where it's going to keep some documentations there if you find that to be more convenient or for posterity reasons. But in this case, I just make it directly in the Gadget folder, and it's perfectly fine to just CP to copy over the binary to where you need it to run it. Okay, so everything made without any problems. So now we see this Gadget 4 hybrid binary that it's going to be what we're going to use to run Gadget. So I'm going to copy this binary to the folder where I have all the other parameter files. In rest. Okay, now I'm going to go back to that folder. Cool, so now this is the list of all the files that you need to run a linear response run. So you need the Gadget binary that's compiled for linear response. You need your growth rate initial file information, and you need the power spectrum's initial information. Need a list of outputs at what scale factor to output the snapshots, and the list of parameters that Gadget needs to read, and also the script for Katana to launch the job. So now you have all these ready, then you simply type qsub script, and now when you check qstat, it should have a job in the queue for you corresponding to the run that you are setting, and check that the resources are requested correctly. So one node, 32 CPUs, 60 gigabytes of RAM, running for 40 hours, and it's currently queued. And depending on how busy Katana is, this could take a while. So let's check the queue. Okay, it looks like there's a lot in the line. So yeah, I'm gonna just end it here. I'll pick it up later when once this run has finished, and I'll show you how to read the results from the linear response run and how to convert that into information that the hybrid run is going to use to input neutrinos into the simulation. Okay, that's it for now.